In associativity, the question is, we have an operator, and which direction is it going to pull its operands from? So in practice, we have something like this string. We have this operator. Is that going to get evaluated before this operator or not? Now, and associativity is completely dependent on direction, right? Left associativity, right associativity. And precedence is different. Precedence is which operators are going to be evaluated first. So we have multiplication and addition here, and with multiplication, we can't say we're going to go right or left or anything like that. It doesn't matter. All it matters is the multiplication gets done before the addition. Now let's look at some examples. So we have here, and for associativity, we have 9 plus 2 plus 3. Here's our grammar. The grammar is left associative because we have the recursion going on the left. And so let's see how that works. So we have 9 plus 2. How are we going to do that? Well, let's first convert all of these digits to D using that production right there. Now we want to use this production. A goes to A plus D. Now let's mess up first, right? So let's change D to A here, and we can do that because A can take the form of D, right? And let's make a new A with A plus D. And now we've kind of got ourselves in a rut because there's nothing that's D plus A. We don't have anything like that. And even if we converted the D to an A, we still don't have an A plus A here. So we got to back up a little bit here. In the future, we'll find smarter algorithms that will take care of it for us. But for now, we're just going to backtrack, and we now have A plus D, which is that right there. And so we can produce a new A plus D in building the parse tree. Now we can do the exact same thing, A plus D. And this will always make plus left associative. Now let's look at precedence. Here we have a 9 times 2 plus 3. And this is kind of cool because the multiplication is going to get evaluated first, and it's on the left, just like it was in some kind of left associative. And so we're going to convert all of these to F's to start with. And then we have a T goes to F times T, so we're going to convert that to a T, and T takes the form of T times F. And now we have a T plus F. We don't have anything that looks like that, but we do have an E goes to E plus T. So first we need to convert our T to an E, so E takes the form of T. And we need to convert our F here, so E plus F. We don't have that, but we do have E plus T, and we can convert F to a T just like that. And we have E T plus, E, let me erase that there. E goes to E plus T takes the form of E plus T. Now you might ask, well, why do we need this whole fancy new grammar? It worked just fine using the associativity grammar. We don't really need these extra non-terminals. And let's look at another example, 9 plus 2 times 3, the second example here. And this is where we're going to see that just using associativity fails, right? So let's suppose that we wanted to evaluate 9 plus 2, and so we convert that to a T, we convert that to an E, and we convert this to a T, and now we get E, it takes the form of E plus T. And now we want E times F. So E times F, well, we have T times F, and there's no way for T to take the form of E, right? So this actually doesn't work. So we need to use the precedence, the power of the precedence in the grammar. And let's look at the last example. It's the same one as this one, 9 plus 2 times 3. And let's look to see how that's going to work. Let's convert everything to an f. And we have t takes the form of t times f. So we want to convert f to a t using t takes the form of f. And now we can take a t takes the form of t plus. Oh, man, I messed that up. What we want is this one, and so I need to convert this to a t, and t takes the form of t times f. Now we can do, convert that to a t, convert that to an e, and we have e takes the form of e plus t, and we're done.